Let me know if you can hear me at home. All right, great, thank you. Oh, where am I? Setting. Okay. Today we start reaction chemistry. And everything we do, with only one exception, this entire term, there's only going to be one exception to this rule. Everything we do is going to look like this. There is a base. It sees the acid and makes a new bond. Okay? Bases make new bonds, and they do that by donating a pair of electrons. Bases are electron, oh, actually, let me do this. Let me change that. Because it's going to make more sense if it's the other one. Bases are electron pair donors. Just saying electron donors is not enough. It is a pair of electrons that bases give away. It is a lone pair of electrons. And we demonstrate that with curved arrow notation. And we make a new bond. So hydroxide, negative charge, lone pairs of electrons, uses both electrons from that lone pair to make a coordinate covalent bond to the hydrogen. Hydrogen, as an H+, as a hydronium, has no electrons. So a covalent bond is two electrons shared between two atoms. But it doesn't have to be an electron from this atom and an electron from that atom. It's allowed to be two electrons from this atom, now shared between two atoms. Okay? Everything that we do, every time you see a curved arrow, you go, oh, that looks kind of complicated. I don't know if I have space in my memory for this. You're not memorizing anything new. You learned this in general chemistry, or you were supposed to. Base sees acid, base attacks acid. Okay, so every time we see a curved arrow is motion of two electrons. Every time we see a curved arrow coming from an area of high electron density, and we're going to an area of low electron density. Okay, super obvious question. How can I tell that hydroxide is an area of high electron density? I can count lots and lots of pairs of electrons. Anything else blindingly obvious about the hydroxide? People at home. Blindingly obvious about the hydroxide that would make it an area of high electron density. Obvious. It has a negative charge. There's a negative charge. Electrons are negative. This has so many electrons, it has a surplus of them. It has actually turned itself into an anion. Okay. Same, obvious question. How can I tell that this is deficient in electrons? It's a positive charge. So if you are lucky enough to be faced with a reaction that has a negative on the page and a positive on the page, it's almost guaranteed that the negative is going to reach out and grab hold of the positive. Okay? I'm writing a little bit small today. I'll try and fix that. Probably, just as probably. All right, let's see what we can think of and start to learn to recognize cases when they start to show up. Because, I said before, 1,600 pages in the book, but only 5 reactions. So you either get to memorize 1,600 pages of the book or you get to recognize what's going on. And the arrow always flows in this direction. We're going to flow from the area of high electron density to the area of low electron density. So, if there is a negative charge, if there's a positive charge, what else can we think of that might go here? This is the most obvious. It is so obvious you couldn't see it. This is the most obvious, a negative and a positive. What else might be in the area right here of things that have lots of electrons? So anything from the right-hand side of the periodic table, your nitrogens and your oxygens, sulfurs, things that have lone pairs of electrons. This is where the reaction is likely to come from. What else might we have that would be an area of high electron density? Have a think. Okay. This is methane. Does methane strike you as something that would have a high number of electrons, high density of electrons? No. It's got 4 boring single bonds. What if I made it a bit more interesting? And turned it into ethane. Is ethane something that you might consider to have high electron density? No. What molecule, not dissimilar to ethane, might have higher electron density than ethane?
Propane.
No, if I make the chain longer, I'm just saying the same argument over and over and over again. Ethene has 4 electrons stuck between 2 atoms. Does that sound like more electron density? It does. This is more electrons shoved into the same space. That's our definition of electron density. How many electrons are we going to get for that volume? This is a high electron density area. When this reacts, it reacts from the center of the bond. When this reacts, it reacts from the lone pair. If I'm showing the hydroxide correctly, I write all the lone pairs in and I pick one and I draw the arrow from that lone pair. That's a lot of work. Drawing 6 dots on a page is a lot of work. Yeah, but if you have to do it over and over and over and over again, so we've allowed this shortcut. You're allowed to draw the arrow coming from the negative. But please be aware that that really is an actual pair of electrons. It really is this. Okay. So, when we write reactions, I need to be able to see where that arrow starts. If your arrow starts here, I can't tell. If your arrow starts here, I can't tell. And if I can't tell, I can't give you the grade for it. Show me where the arrow comes from. Show me where the arrow goes to. Well, if alkenes are high electron density areas, what else could be? Would be absolutely no reason why an alkyne couldn't either. Yeah. And look at this. If I take a pair of electrons out of this alkene and do something with them, those carbons are still connected to each other with the sigma bond that is underneath the pi. So it's going to be the pi bond that moves. It's the pi electrons that are given away. The sigma electrons hold the framework of the carbons together. The pi electrons are your area of high electron density. Okay. What could we possibly have here? Anything with the positive. All right, here's how we figure that out. Remember that part when we were writing Lewis structures? And we said hydrogen always makes one bond, right? This one doesn't. This one doesn't have one bond. Remember that part where we said oxygen always makes how many bonds? People at home, how many bonds does oxygen always make? 5, 4, 3. Yes. That should just be an immediate automatic answer. Oxygen always makes 2 bonds. There's oxygen always making 2 bonds. What happens if it only makes 1? Have to put a negative charge on it. What if it happened to make 3? Yeah. So if I put more bonds to an oxygen than it's supposed to have, it picks up a positive. I didn't need to erase that, but I just did. So if I were to see, I'll write it the other way. So if oxygen makes 1 bond is a negative, 2 bonds is 0, 3 bonds is a positive. Would that hold true for oxygen's neighbor? Oxygen's neighbor is nitrogen. Nitrogen is nitrogen. This is in group 5, we're told always makes 3 bonds. What if you made 2 bonds to a nitrogen? Would you have a charge? People at home, 2 bonds to a nitrogen, would it have a charge? And if so, what sign would it be? Yeah, 2 bonds to a nitrogen makes that nitrogen negative. 3 bonds to a nitrogen makes that nitrogen neutral. Not in terms of pH, but in terms of charge. 4 bonds to a nitrogen makes that nitrogen positive. So things that could be on the receiving end be this. Now, our rule breaks down a little bit when it gets to carbon, because carbon is different than oxygen and is different from nitrogen in that it doesn't have a lone pair of electrons. Carbon always makes 4 bonds. If I take a bond away from a carbon, NH4, yeah. That's plus, and an N, and an H, and then a subscripted 4. Ammonium. Carbon, this one's a bit trickier. Carbon always makes 4 bonds. Could I ever put a positive on a carbon? That's Jenny. So what I've set you up for is for you to say no. Yes. Yeah. But oxygen and nitrogen are different from carbon. What I need to do is break one of these bonds. And the way that I break it is going to determine what happens next. This is methane. And I decided that I wanted to lose H plus. How many electrons does H plus have? None. None at all. H, the atom, is H dot. Hydride is H dot dot. And H plus is the absence of the electron. Hydrogen has 1 electron, the atom. If I make it into H plus, it has no electrons at all. So if I want this molecule to give up H plus, it leaves its electrons behind. And I get a negative charge on a carbon that is called a carbanion. Carbon anion. Stuck together. Okay? On the periodic table, other than hydrogen, what other things always make 1 bond? Okay. What else from the non-metal side? Because we're looking at covalent chemistry. The halogens. Very good. Okay. So I'm going to do the same thing again, but I'm just going to make it a little bit more obvious. What if instead of methane, I had chloromethane? When this molecule breaks, do you think it's going to make Cl plus? No. With only general chemistry behind us, that just sounds wrong. What ion does chlorine make? It's in group 7. It makes the chloride ion, which means it picks up a negative charge. And that negative charge arises when the bond breaks on the other side of the pair of electrons. And this chlorine takes both of those electrons with it. Chlorine was a chloro group in a covalent bond. It had 7 electrons. If it steals an electron, it gets to be chloride, has a closed shell configuration. So it steals an electron and leaves a positive behind. Oh, that's an R. And that leaves you something called a carbonium ion, now widely called carbocation. Okay? This breaking of a bond where it is uneven and the electrons decide which of the parents they're going to go and live with after the divorce, that's a heterolytic cleavage or heterolysis. That is an uneven break. And both the carbanion and carbocation are generated by an uneven break. So if I could put a halogen into a molecule in such a way that it's okay falling off and leaving, I can find a positive charge, I can find a carbocation, then I can make the reaction come to it. What if the leaving group hasn't left yet? Hold on, just a second. Got the keys?
Thank you.
If instead of making the carbocation, I have the thing that is about to make the carbocation. Bonds can be polar. That bond is polar because chlorine is what? What is it about chlorine? What is that one word about chlorine that's going to make that bond polar? It's electronegative. And electronegativity is what? Definition of electronegativity, people at home. What is that? The tendency for an atom to pull electrons towards itself. Electronegativity is the ability to pull electrons towards yourself within a covalent bond. Chlorine is on the right-hand side of the periodic table, so it pulls it away from chlorine. Carbon, chlorine, electronegative. Carbon, not. This bond is polar. The electrons are now here, much closer to the chlorine than they are to the carbon, which makes the chlorine a little bit lowercase delta. Delta is change. Lowercase delta is a small change. So this chloride goes a little bit negative, which leaves the carbon a little bit positive. This molecule, in the presence of hydroxide, my arrow goes to that carbon. Okay? Because that carbon is now an area of low electron density. So you can be an area of low electron density if you are a carbon and you have a positive charge. That one's obvious. But you also get to be an area of low electron density if you're attached to something electronegative. So carbons that are attached to an electronegative atoms are targets. These can't all be bases. They can't all be acids, right? So there's an overarching name. The bases in this scheme are now called nucleophiles. And the low electron density places are called electrophiles. And in a reaction, the nucleophile reaches out with a curved arrow and gives 2 electrons to the electrophile. The base reaches out and gives 2 electrons to the acid. So as complicated as this is ever going to get, and there will be times when you think, this looks too difficult, it comes right back to a hydroxide and an H+. It's always the same thing. Find the base, find the nucleophile. It's the thing with the electron density. The other thing on the page is the place that's going to get targeted. And sometimes it's going to be obvious, and sometimes it's going to be subtle. And the subtlety is, oh, you're next to something, and that something is pulling electrons away from you, making you deficient. All right, let's do some. The last thing that we looked at was alkenes. This will be a good place to start. Let's keep it nice and simple. Here's ethene. Ethene has a sigma bond. And then on top of that sigma bond, it has surplus electron density in the shape of a pi bond. It makes this alkene be unsaturated. Okay. Let's figure out if we can predict what it is that this alkene is going to react with? Do you think that the alkene, time for a poll. I haven't had a poll. Let's do a poll. Alkenes, are they going to react with acid or are they going to react with base? Come on, 10 of you haven't voted yet. Got to move on. Okay, in the room, are the people at home right or wrong? Remember, did we do one on Monday where everybody at home was wrong?
Yeah.
Like every single person was wrong. There was one holdout and they swapped their votes at the end. Oh, that's kind of fun. Oh, well, it's getting neck and neck. It's getting neck and neck. All right, I'm closing this in 5, 4, 3, 2. Closed. What was that? This makes this an area of high electron density. Areas of high electron density were bases. Bases don't react with other bases. Bases react with acids. This alkene is going to react with an acid. Keely, name me an acid. Simple one. Really, really simple one. Give me the front and the back. Name me an acid that you learned in general chemistry. The one that everybody knows. Yeah. Here's hydrochloric acid. Hydrochloric acid is polar. It is polar in that direction. Because chlorine is electronegative, group 7. Hydrogen is electropositive, group 1, which means the hydrogen end of this molecule is positive, and the chlorine end is negative. And in fact, if you were to put this in water, we're not in water because oil and water don't mix, and my alkene is an oil. If you were to put this in water, they would separate completely into H plus and Cl minus. In the gas phase, hydrogen chloride is a covalent molecule. This is polar. It's a polar molecule. Okay. People at home, people in the room, draw your very first curved arrow. I need to see where the arrow starts from, and I need to see where the arrow ends. People at home, you have a blank whiteboard. Go. It's a race to see who can do it first. Don't really need the dots. It's fine if you put them. You're not going to get graded off if you don't put them in. There you go. Ah, person writing at the top. I like where your arrow started from. Not too happy about where it finished. Because it looks like it's going to the bond between the hydrogen and the chlorine. And there are electrons in the bond between the hydrogen and the chlorine. That's not the most positive part. Yeah, that's not the most positive part of the sketch. Come from the most negative part, the center of the double bond, to the most positive part. Chlorine is there you go. Chlorine, the person at the bottom. It's like, yeah, they're struggling, but they got it. All right, good. Good try, both of you. This happens. Here's my area of high electron density. Here's my area of low electron density. My arrow comes from the center of that bond and goes to the hydrogen. I've successfully made my first curved arrow. But how many bonds is hydrogen allowed to make? 1. Hydrogen already had a bond, and now you're making a new bond to it. So what does it have to do? You're only allowed to hold hands with one person at a time. You're holding hands with the charming person to your immediate left, and then a more charming person to your immediate right comes along. You have to dump, okay? Which means this bond is going to break, because this hydrogen can only make one bond at a time, and it has decided to accept the offer of a new bond. It has to break this bond. So there's another second curved arrow. And that curved arrow starts here at the center of the bond where those electrons are. Where is the arrow going to end up? Yeah, Rebecca, it's going to the chlorine. What I'm essentially doing here is making an H plus that the carbon takes and a Cl minus. And how do I turn a Cl into a Cl minus? Well, I give it both of the electrons that were in that covalent bond. This is heterolysis. That is an uneven split. This bond split, and both the electrons go to stay with the chlorine. Okay, that's our first step. And we draw first steps by drawing horizontal arrows. So you get a horizontal arrow between here and here. I might actually run out of space. I'm going to make this a little bit smaller. Okay, horizontal arrow means reactants on the left, products on the right. Okay, so the arrow came from the bond that was between two carbons. This hydrogen is going to be attached to one of those two carbons. Can we tell which one it is? The answer could be no. No, the answer is no. And the answer is no because my starting reactant is symmetrical. So attaching the hydrogen to the left or attaching the hydrogen to the right makes no difference. Makes no difference. Pick one of the carbons. Attach the hydrogen to it. Now that hydrogen came attached. It didn't bring any of its electrons with it. So it attached as an H+. There's a positive in this molecule now. This is a carbocation. And there is a negative on that group right there. This, all of this, had no charge. This, all of this, has no charge because the pluses and the minuses have cancelled each other out. When you're writing something, if you create a new charge, you have to keep them balanced, okay? You have to have the same number of charges at the beginning that you have at the end. All right. Guess what happens next? I have two things on the page. One of them is going to attack the other one. Make that happen. People at home. Make that happen. I will get you started. Okay, people at home, finish it. Come on. Show me exactly where that red arrow started. There you go. That's it. That's it. That's all you need. Okay. Shutting that off.
That's a curved arrow.
It's a curved arrow from the negative area of high electron density to the positive area of low electron density. What's the name of the product? Chloroethane. Don't need the one because there is no such thing as a two. No, don't apologize because one chloroethane is better than, having it and not needing it is better than needing it and not having it. This is chloroethane. I started out with an alkene, and I have generated a haloalkane. Both of these classes of molecules have entire chapters in the book. So I've just managed to take something from one chapter and generate an entire chapter's worth of material. I've changed the functional group in this molecule. This was unsaturated. My product is saturated. It contains only single bonds. Okay. Way back from your general knowledge, general chemistry knowledge days, we did reactions that were combinations. We did reactions that were replacements. We did reactions that were double replacements or double displacements. If you had to think of a name for this, what kind of a name would you give this?
Is it a double replacement as you take the double bond away?
No, a double displacement or double replacement is acid-base. It is acid-base chemistry, but it's when you switch the tail end of the base for the front end, it's an ionic thing. This is an addition, it's a combination. The general chemistry texts will allow combinations or additions to be the same thing. It turns out there's going to be more than one flavor of addition. This one is an electrophilic addition. So we name the reactions based on what the other thing in solution is doing to our chemical. Our chemical is the alkene, and it's the electrophile that's causing it to react. The electrophile is this positive part right here. How am I doing for time? Oh, I'm over. You got to let me know when I go over, because the clock at the back of the room says I'm not done for another 2 minutes. We're going to have to change that clock. This is an electrophilic addition. More on Friday. Lots more. Because do you think this is going to be different if I change the alkene and change the acid? Not significantly. Okay? So Friday, we're just going to pound electrophilic additions into you. Okay, apologies for going over. Yell at me when I go over, because the clock in the room is wrong. Gradebook is almost up to date. There's still a couple of you that haven't had one of yours graded, but I had a bash at them yesterday and they're mostly done. Part 2 of everybody's exam has been graded, and if it wasn't perfect, you get a little comment that says, take a look at this. This is the bit that you need to concentrate on in fixing it. Okay? And I sent out a message about lab. I'm splitting the data collection for the lab between Tuesdays and Thursdays. When Thursday's lab collects a bit more data, we'll give everybody in the class the data in which to do the write-up. Okay? All right. See you Friday.